We need to understand that there are two major approaches to seismic design. One is force-based design, and the other is displacement-based design. The force-based approach is the traditional one, and it's still the basis for most of the common design methods used today. On the other hand, performance-based design, which is kind of the next generation approach, actually combines both force-based and displacement-based concepts. Let me explain how the force-based method works. In this approach, we start by estimating the loads acting on the structure, including the loads caused by an earthquake. Once we know those loads, we apply them to our structural model and calculate the internal forces in each member, like axial forces, bending moments, and shear forces. Then, we design each member so that its strength or capacity is greater than the force demand it needs to resist. Basically, we check whether each element can handle the expected forces. If the capacity is greater than the demand, great, the design is okay. If not, we need to strengthen that member, maybe by increasing its size or changing the material. On the flip side, if the capacity is way more than the demand, well, that's a sign the design might be uneconomical, and we could probably optimize the structure by reducing some of the member sizes. So yeah, this whole approach is based purely on forces. But there's another way to look at it, and that's where displacement-based design comes in. Instead of asking, how much force is acting on this member, we ask, how much is this member going to deform, and can it handle that deformation? In performance-based design, that's exactly the idea. We realize that looking at deformation gives us a more realistic picture, especially under strong earthquakes. Why? Well, here's the thing. The forces we estimate using force-based design are just approximations. And in reality, the actual forces that a structure experiences during a real earthquake can be very different from what we estimated. That means a design based only on force estimates might be either unsafe or just unnecessarily expensive. Plus, different structural members behave differently. Some are more sensitive to force, others are more sensitive to deformation. So, for members where displacement is the controlling factor, we need to evaluate and design them based on their deformation demands. And for those where force is the critical parameter, we stick with the force-based checks. In displacement-based design, we estimate how much each part of the structure will deform during an earthquake, and then compare that to its deformation capacity. If the demand stays within the capacity, we're good. If not, then adjustments need to be made. Alright, so just to quickly sum things up, most current design codes still follow the force-based approach. In this method, we assume that the forces acting on the structure are elastic, and that the structure itself doesn't go into nonlinear behavior. We'll get deeper into this later. But for now, here's the point. To somehow account for that nonlinear behavior, which in reality does happen, we apply reduction factors to the estimated seismic forces. And why do we do that? Because experience has shown us that the forces a structure actually goes through during a real earthquake are often much lower than the elastic forces we calculate. So these reduction factors help us approximate that more realistic, inelastic response. But at the end of the day, force-based design is still focused mostly on strength, not on performance. And that's where this method can fall short. Just because a structure is strong enough doesn't mean it'll perform the way we want it to. Its actual performance could end up being very different from what we expected, especially in a strong earthquake. Now, contrast that with the displacement-based approach, which forms the backbone of performance-based design. This newer method focuses on how the structure really behaves, how much it actually displaces, and how much damage it might experience. It directly considers nonlinear behavior because, well, that's the real-world behavior of buildings during earthquakes. And instead of only checking strength, it puts the spotlight on performance goals, like minimizing damage, protecting life safety, or making sure the building stays usable after the quake.